this is really a talk of many pieces. If people come in late, then, they'll just miss one of the pieces. I think that's okay. And we've got a lot to cover. I'm not sure I'll get all through it. I'll move as quickly as I can. I'll probably put some blog posts out with these in as well. So if I don't get to everything, don't panic. I'll figure out a way to get the information out there. But anyway, so first of all, thank you for coming, because I noticed that my talk didn't have an abstract until 2 days ago, and I don't think it had one on the app until 1 day ago. It just said abstract here. So I'm not sure what went wrong with that. And if you're wondering what this is about, I figured monads would be well and truly covered at Scala Days. I'm not against monads. In fact, I did a talk about them in Devox in Java 8 just a couple of days ago, or a few days ago. But I thought I'd like to take this crowd and do something a little bit different and kind of show you some of the patterns that I use day to day that are non-monadic, but fit very nicely with the current trendy that Hansel, he's so hot right now, topic of monads. So a little bit about this. Oh, I need to be in full screen over here. That's why that's not working. Okay, now we're good. Right, so NoMonads, NoSQL. I actually came up with this term a few days ago. If any of you know art or know something about art, there was the Impressionists, and then came the Post-Impressionists, and then there were the Modernists, and then came the Postmodernists. I wonder if you can see where this is going. At this point, I've been through the trial of fire that is Monads. I worked with Runar Bjarnason, to my great credit, who, yeah, there he is. Hey, Runar! Who is actually, don't let him fool you, is a wonderful teacher, actually. He'd make a great teacher if he put his mind to it. And what I consider myself now, perhaps a little arrogantly, is a post-monadist. I think that what I've seen, many times in my career, is lots of people are suddenly talking about something, and, the silver bullet kind of comes up in that. It's like, oh, this can do anything. And my experience has been there really are no silver bullets. Even silver bullets, actually, if you look at the legends, aren't really silver bullets. They only kill, werewolves, and then, depending on what you believe, only certain werewolves. But one thing I have found, whenever anybody talks about a technology like that enough, there's some value in there, and you need to go and look at it to see what the value is. And then you need to step back and you say, well, how can I use that sensibly? How can I apply that to solve my problems? So in this, I'm kind of looking at this as a not only monads. Just like NoSQL is supposed to be not only SQL, this is a not only monads talk. So why and why not? We'll cover those in a second. And then I want to talk a little bit about Occam's razor, which is still something that I learned very early on in my learning. By the way, can some of you guys sort of move over a bit so that people who are standing can sit, please, pretty please? You're all really friendly by this stage. You should be after 2 days. So, right, so Occam's razor refresher. So, monads, don't get me wrong. I use and like them. Who doesn't? I mean, who doesn't use option or list here, for crying out loud? And futures, right? Everybody's using futures. They're fantastic. I also know, though, that I've got a lot more tools in my toolbox than, in particular, writing a new set of monads. And in Scala, I really feel we should embrace Scala for its Scala-ness, okay? It is a distinct language from many of the other languages that we use, and in particular, object orientation is in there, and it's useful. It can solve some real problems. So that's the kind of, monads give you incredible cosmic power. They really do. You can do just about anything, right, Runar? Yep, exactly. Flat map that shit. But sometimes you just get the impression that you're trying to use a sledgehammer to crack a walnut. And perhaps it's worth pulling back from that. I've seen some perhaps less well-advised uses of, in particular, free monads in the past that just make something far too complicated for what it needs to be. In particular, I think that probably one of the more amusing things is somebody trying to recreate BASIC using monads. And I'm looking at that going, well, you could certainly do it. Why? Yes, that's perhaps why not. So why would you not? Sometimes, as I say, it's overkill. This one I think is more important. Monads don't mix well. You have to really consider if you're bringing in a bunch of different monads. By the way, this is what happens when Darth Vader tried to mix monads. He doesn't look very happy, does he? No, this could be you. So you really have to figure out, I think the happy point is you want to figure out what your big rock is. If you've got something that you're wanting to use monads for, that ought to be the big thing on the project that you're trying to solve with that. And then some of these other patterns can fill in around the edges without interfering with that. And actually, again, Runar taught me a nice little way around this as well. Monad transformers, a bit hairy, but I do like his idea of compiling monads down into other monads. That one works nicely. So you can take your own free monads and turn them into like task in Scala Z, for example. And then you can have another free monad that you've written that also compiles down into Scala task. Now you're not mixing them anymore. Now you can actually use them together, which is nice. Ease of use is another one, and when I say that, this is a difficult one to really get your head around. But I want you to ask. I want to ask your patience for a minute while I explain what that means. I work primarily on a project that involves a lot of bioinformaticians, very, very smart people, frighteningly smart. At least in one case, he's actually mastered Scala Z streams pretty well at this point. The thing is, they're not interested in the shit we're interested in, okay? They're trying to actually do something with genetics and stuff like that, and anything that gets in their way is not good, okay? They need something that just lets them do what they want to do. Monads are great if you can make them part of the solution, but not if they're part of the problem. And in particular, it's nice to have an environment that they're guided through writing the thing that they're trying to write. And the enormous cosmic power of monads means that when you get them in there, they're like, well, what do I do now? And it's not clear. There are actually, what I actually ended up doing for a library that Runar and I worked on was wrapping it in a API that actually kind of led you through the process of using it so that you knew roughly what to type next or what the options were for typing next. So that's one of them, definitely ease of use. And pragmatism, the flip side of that is when things go wrong, and they do. Certainly option and list at this point are pretty reliable, but other libraries that I've used have actually exhibited errors and bugs. They're really hard to track down when that happens, and the compile errors are definitely not something you want a bioinformatician to see. They always call you and they're like, what the hell does this mean? And so, yeah, pragmatism is not a bad word. It's literally the way things are. And things like IDEs, code completion, even debuggers and discoverability of an API are all your friends, particularly when it comes to supporting clients who are not interested in computer science. Okay, so that's my case. Occam's razor. Actually, the original definition is quite arcane, but roughly speaking, it's the simplest solution that fits the facts, is the current one until proven inadequate. Einstein's sort of take on this, incidentally, I like to mix things up. That's Einstein. Everybody thinks of him as the crazy guy with the big hair, but he was young once too. Everything should be made as simple as possible, but not simpler. So a quick story about this. While I was working on this big project, we had, being Scala, it attracted a lot of people from the functional programming community. Some of these guys were working on the visualization side of the thing. And while I was there, they were saying, well, we need a better language to describe, the graphical components and the layout and stuff like that. We should use monads. And at the time I said, I think what you really need here is just a bunch of case classes and some builders and, make it nice and simple, make it very clear, make it chain, a fluent interface, fluent API, that kind of thing. And they said, no, it won't compose. Actually, the conversation went something like this. I said, what won't that do that they need to do? And the answer was, it won't compose. To which I said, do you need it to compose for them? And I never got an answer to that. They just ran off and wrote the Monads library. So it got written. It got used for about 2 months. Everybody decided it was too complicated, and it got basically pulled out and rewritten as a bunch of case classes with some fluent builders. And so, yeah, another one is premature optimization is the root of all evil. I would add my own little coda to that, which is premature overgeneralization is the root of a little bit at least a little bit of that evil. So don't generalize too early. You know, if that's what works to start with, you can always write the bigger one later if you need it. Okay, so let's have a look at some of these. And I'm going to start with stuff that you'll be going, oh, Christ, why did I come in this, into this one? The mighty case class, okay, super low-hanging fruit. The reason I mention this is it gets overlooked as a very powerful API creator. It's a great basis for an API. You know why? Because everybody, as soon as they start Scala, no matter how far they are into it, they immediately understand what case classes do, and they immediately understand the value. Okay, pretty much everyone. They're all like, hey, these things are cool. Okay, and they grasp them straight away. Why, if you can, would you not build an API around something like that until it doesn't work anymore? So that's an example there. This is something I do a lot, is just introduce types. Type early, type often in Scala, okay? Instead of passing strings around and ending up with a stringly typed program, simplest thing you can possibly do is just make a type around that value. And, you know, now you've got types, now you've got a whole bunch of new dimensions. And I'll show you how you can then take advantage of some of that in a minute. So that's the mighty case class. And of course, case objects are the flip side to that. Now, case objects, just to give you a sort of sense of where I might be going with this, there's one thing about objects, which is there's only one of them, ignoring class loaders and stuff like that. There's only one of these things. That means that you can actually put, fairly guilt-free, a ton of information into these things without worrying about resource problems. Okay? You can basically pack the kitchen sink into an object and not worry about the fact that there's going to be tons of them in memory and you're going to run short or anything like that. So that's a real advantage. If you can get it into case classes and objects, you can actually get quite a lot there. Another one that I use a ton, and by the way, I am going to talk about the upsides and the downsides of these patterns. I write a ton of loans. Loans are one of the patterns that I just reuse and reuse and reuse. Typical loan is it's basically resource management. It's to make sure I don't forget something when I use, something that needs to be closed or cleaned up or something like that. And it's a super simple thing. Scala has great syntax for this. So there's a loan that you give it a file name. It gives you a print writer. You use the print writer. You don't have to worry about creating the print writer. All those layers of file. It's not too bad with print writers, but the Java file API is crazy. Like open a buffered reader over a file reader over a blah, 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 blah. You can do all that, and then you can clean it up afterwards and never have to worry about it. So I said I was going to talk about some of the downsides. Here's another one. This is a loan that has a return type. It has a generic return type. I wonder if anybody is going to smile or chuckle at this point, because you might know where it's going. Okay, well, I'll keep going. So, as I say, I use loans a lot. I tend to use them internally. I tend to use them for my own purposes a great deal. When you make them part of a public API, you really have to think about what you're doing. So I did this. I actually created just a with iterator. I wanted people to be able to iterate over something, not worry about the cleanup, not worry about closing the file afterwards. The idea was they would get loaned the iterator. So what do you suppose that the bioinformaticians did when I did this? Anyone want to guess? Yes, they immediately returned the iterator from the loan block, at which point it's been closed and no longer works. So you end up with bad file descriptors all over the place. And I thought, wow, I never thought about that. Why would they have done that? Because they're looking for the easiest way they can possibly write something. And they're like, well, there's an iterator here. I'll just pass that back out. So, lessons learned there. Probably not a good idea to have a generic return type on an iterator on a public API. Because it's going to get abused. Okay, so think about what you're returning if you use them. What I tend to do these days is actually use other mechanisms on public APIs, but I still use loans totally all the time internally because they just make my life easier, even if it's not part of the public API. All right, type parameters, type early and type often. Should be a motto in Scala because it can save you an awful lot of trouble. Another real-world problem with a simple solution was that we have a database query language. Actually, this is the monadic library that Runar Runar created and I helped with. And within that, we have queries. And one of the things that, this is Couch, so I don't know if you know Couch. Couch has a design document, which is the kind of overall grouping. Then it has a view name. And obviously what we want to return from that is some kind of rich data type. We could just return the JSON, but really what we want to do is do the type class conversion back into the actual return type that we're looking for. Now the thing is, in our system, as in most sensible systems, the design doc is tied to the class that you want to get back out of this thing, right? If you've got a person, your design doc is going to be called person. You might as well call them the same name. They've got to be unique anyway, and it just means that you have less confusion about which is which. And the problem was, with copy and paste being what it is and stuff like that, quite often the bioinformaticians would have a design doc and a different return type, and then suddenly they get either a problem with being the wrong return type, or the design doc doesn't have that view in it because they've got the two separated, the two have diverged. That, as I said, that usually happened as a result of copy and paste. But there's an easy fix for this, which is just to encode the type into the class that is representing the query. Okay, now you can use that with manifests, although actually I was going to go back through, I ran out of time on the slides. Really you should be using class tags and type tags now, and in fact this could be a class tag here. You don't need the full manifest, but at least this code is based on 2.10 right now, so type tags are not entirely recommended use or thread safe at the moment. In 2.11 I believe they're fixed, so I'm looking for confirmation, but somebody told me, Jason told me that they're ready to go now. So anyway, by doing this, you no longer face that problem of divergence. And when you write the query, which I think I have on the next slide, the query can infer that type from the query that the query method can infer that type from the query case class that you're passing in. So that's just some low-hanging fruit that solves a problem right now. Okay, get your types in there as early as you can, and kind of let Scala do the heavy lifting. Okay, generic pattern matching. This is another one that I use occasionally, and I feel a little dirty doing it, but fact is I'm often pulling things out of databases where there are no types and trying to get them into places where there are types. And basically the best thing you can do is try and do that as early as possible. So the moment you get handed some kind of string of JSON or whatever it is, you immediately get that thing into the type system. And this I'll actually give a concrete example in a minute, but here's the classic problem. We've got a doohickey that holds onto a parameter of type T, and then we want to combine it with another thing that we're going to get passed in, an any, and we want to do a pattern match to see if it's the same kind of thing. And if it is, it also takes a combiner, how to combine one of these things that we've got with another thing of the same type. And in the case of the other thing being a T, we can call the combiner. In the case of it not being a T, we're just going to give back none. So it's an option. We give back either some or none if we can combine it. When you compile this, you obviously get the first warning that something's wrong, which is the eliminated by erasure warning. Basically, what it's telling you there is, it doesn't matter what any is, it doesn't matter what T is, that first pattern match is always going to match. Okay, it just can't tell. It's going to say, yes, this is one of those, I believe you. Now, this may come as, I don't know, some of you may be surprised by this, but, oh yeah, this is it in use. When you get it, you get a class cast exception in Scala. Now, this still came as a surprise to some of the people I've talked to that didn't know about this trick, but if you include a class tag or a manifest on that, the pattern matching actually starts working again. It can tell. Scala's compiler knows enough about class tags and manifests to be able to do that comparison properly on a pattern match. And I promised you a real-world example of where we use this, so I'll tell you that right now. We have, like many NoSQL database users, we have the need for foreign key references, IDs to other types in the system, but we don't have a typed system, okay? And we don't have real foreign key references. So what we end up with is strings in the string references to other IDs in the database. And when you get those, within the containing object, the containing data record, you have that ID, and you want to say this is an ID to a person. So you actually have an ID of person in there. But it's just a string, okay? So what we do is we basically have a possible or a potential ID to a person, and then we kind of reify that into an optional person in the type system, and we use this to do that. We use a manifest to say, okay, what type am I expecting this to be? Can I pattern match against it? And then we try and get that item out, and then we try and serialize it in. If any of that stuff fails, you get a none back. Okay, but now you've actually encoded this ID back into types. Okay, it could be none. It could be that it's a bad reference or a reference to something else. But at least the programmer knows if there's something there, it's going to be the right type. So that's an example, and lo and behold, that works. So that's the generic pattern matching. Okay, types again. So here, just create a new type. What am I saying here? Yeah, this is Couch ID. The reason I brought that, ID, the reason I brought that one up is if you don't know all of the possibilities of the things that you could be referencing, which is our case, you can't do this. But in a lot of cases, this is a better solution, which is to simply provide a new type which wraps the deep type of the thing that you're trying to pattern match against. So if you do this, if you create a string list and an int list, these are bad examples, but apply them in the real world and you'll see the value. Then we know, in the case of this being a string list, the only thing it could have in it is a list of strings. We don't need to do manifests and things like that. We know the type because it's now been encoded into the case class. Right, next one, Immutable Builder. This is another one that I use all the time. Immutable Builders I love because they guide people through writing these things, okay? As I said, case classes are a wonderful, easily accessible way into Scala. Everybody gets them immediately. I've taught loads of people Scala. Everybody gets the value of case classes and how they work immediately. And case classes actually give you, with virtually zero effort, a bunch of stuff right out of the box. So the default named parameters, for example, give you something like this, where you can just say HTTP connection of server, and all of the other things are the defaults. Or you can just write, and IntelliJ will give you the list of options. The IDE will give you the list of options of what you can put in here. So I can specify a port and whether the SSL is on, and username, or username and password and credentials. All of that stuff just leads you through writing it. But here's the trick. If you want to go a bit further and you want to put a bit more work in, you can go even further than that. So another example is the fully guided creation of something using an immutable builder. Something like this. So we create, at the end result, we want a defined SNP, a single nucleotide polymorphism in genetics terms. It's just a way of talking about a mutation in genetics or in the genome. That's where we want to get to. It has to have a name, a location, and alleles. In practice, they have quite a few more fields than this, but it didn't fit on the slide when I did that, and you get the idea. And what you start with is just a SNP object, case object, and then you write this little Fluent interface that just says, okay, now you've got to name it. So now you give a name of a string. That ends up being a named SNP. The next thing you need is the location. So now you get a named located SNP. Then from the name located SNP, you get to a defined SNP and so on. And the great thing about this is it literally writes itself. It's like, okay, somebody needs a SNP. They write this, they hit control space, and up comes named. That's the first thing you've got to do. Okay, I'll name it. This is great for people who aren't interested in the stuff that we do. Okay, that's the real key here. That's the takeaway, is just because people are using your stuff, don't make the mistake of thinking that they care about it. Okay, they really don't. In fact, they will care more about something that you can do for them than any amount of, hey, look at what I did. Isn't that cool? So those are easy things. Okay, type classes. Anybody not really familiar with the idea of type class? Because I will go over it. Yeah? Okay. Very, very quickly. Type class is a class that has a type parameter. It applies some behavior, some ability to that type. And a classic example, this is JSON or spray JSON, which I use a lot. The idea here is starting from a case class that has nothing special about it. It's a bog standard ordinary case class. We can define an implicit format, a type class for that case class color, and it says this is how you turn yourself into JSON, and this is how you reinflate yourself from JSON. And in this case, JSON Spray, or Spray JSON actually makes that very easy by providing you with these little JSON formatters that work over case classes. And I'm going to get to more examples of this, but the nice thing, again, the nice thing about case classes is they have a lot of helpers that let you do this kind of thing. You can actually use kind of introspection techniques and things like that to write convenience methods so people don't even have to write the writers and readers. But without this, and I'll show you in a minute, you would actually write some kind of implicit, probably a val or an object, that has two methods on it, which is write one of these items into JSON and read one of these items from JSON. So one way it's takes the item, returns JSON. The other way it takes JSON and returns one of those items. And you have to supply that method. Once you've supplied it, you can have a method that implicitly or context bounds it. Basically says, I'll take anything, I'll take any generic, as long as one of those formatters is available for it. And now the compiler knows that you can call read and write on it, so you don't have a compile error anymore. You don't have any of the kind of reflective concerns that are a problem. So that's type classes in a nutshell. So now I'm going to introduce another one. This one's, and I should say at this point, I put these kind of patterns up there all the time. I've done patterns before that I now think were a really, really bad idea. That any of these at any point could be, oh, I didn't think of that. That's really not a good idea. So, 2 years' time, I come back and do this talk, and I'm like, yeah, I told you to use that one. Maybe that's not such a good idea. But this one's been useful to me so far. So this is basically extending builders so that they understand rules of, something about the state and something like that. And in this case, this is another one of those queries that we use with Couch and the Couch library. And what this has to do is build up a whole bunch of parameters. These things all get encoded into a great big long URL encoded query that Couch uses. But there's a few rules, like, for example, if you have a reduce, if you make this a reduce query, you cannot request documents or grouping anymore. That actually causes an error in Couch because those things are not compatible with one another. If you're doing a reduce, you can't get the individual documents because there are no individual documents to get. It's been reduced. So when I do that, you can actually encode these kind of rules into the builder as you write them. So here we have a reduce that just says, well, if it is actually being reduced, if we're turning reduce on, then we have to get rid of the group and the include docs and then add the reduce. Otherwise, we can just set the reduce to false. So you can encode rules, and you can get quite sophisticated with that sort of thing. The whole idea of this is all of the parameters are just an immutable map, and every time you add a parameter to this, it just makes a new copy of that map with the new parameter in it, and then gives you back a new one of these queries. So the old one is left alone, but you kind of roll forward, building up the query with all the things that you want in it. All right. A case with paired type class companion. Okay, so this one is, and this is quite a long example, so I'll just plow ahead. We'll see where this is going in a minute, but let's say we start off with just an abstract database object that we want to get out of our database. And all we know about it is that we're going to take the manifest for this guy. This is intended to be a superclass for an object, not individual instances. It's not clear, but it doesn't really need to be at this stage because this is internal stuff that we deal with. I'll show you the more public one in a minute. So we make a sealed abstract class, abstract DB object. We've got the manifest if we need it, and you can see there, what I do is just shove the manifest in. Now, manifests are quite heavy, and I'm sure the same is true of type tags when I get to use them. There's quite a lot of stuff depending on the depth of the data structure that you're representing, or the type that you're representing. There's quite a lot of stuff in there. But since this is an object and there's only one of them, I really don't care, and I'd rather have it stuck here than showing up in a bunch of different methods in the code. I can just stick it in here. This thing's going to be a type class. That's why it has a parameter. And so I can stick it in here, and I can look up the manifest whenever I need to use it. So pretty low cost. The manifest gets created and shoved in there one time, and we've got it there for all time. And then down here we've got a method that gets JSON. Obviously, this would be something like query the database, but what it says is, I'll take any type as long as there's an abstract DB object defined for that type. And here, because we know that, we can now implicitly get the companion for that, which is the the guy there. And from there, we can get the type manifest. And it also extends JSON format, which is our spray JSON type class. So we know there's going to be a read and a write in there, and we know we can write it as JSON and read it as JSON. You can get as sophisticated as you like with this. You can layer up multiple type classes in one, and probably you want to, because that saves you having context bounds, context bounds, context bounds all the way through, which ends up in some pretty long type signatures if you do that. So if you get that, just inherit them and combine them into one. Here's the actual use of this. Now, we're into the world of, 1 to 22 fields at this point. I'm showing the two case, the case of two type parameters. The case of all the others is left to you, but I will tell you there's a catch with 0 and 1 in some of the methods like apply and unapply. But anyway, there's a few things going on here. So this extends abstract DB object, okay? But now what we're going to say, and this is really interesting, we can define apply and unapply as type signatures, but leave them as abstract. And what does this do for you? Well, the key thing here is when you define one of these over a case class, apply and unapply are generated for you with these type signatures. That satisfies those abstracts. So now you know you can use those, and you know you can use them to get those types. This is where it starts to get clever. The other thing that I couldn't believe that you could do, I tried it, and I'm like, wow, this works. It felt like I was getting away with something, and then I'm like, I'll wait for it to seem like a bad idea, and then I'll give up on that. Was the whole idea with type classes is you make them implicit so they can be filled in as implicit parameters. And in the case of a case object, or in the circumstance of a case object, the companion object for that case object is searched when Scala's looking for an implicit to satisfy that. It looks inside of it. The thing is, I didn't want to have to define an object and then define the implicit inside of it. I just wanted to define the object and have it extend that type class and fill in anything it needed. And as it happens, it doesn't actually have to do anything. But I need it to search for that when I use that case class. And the way you can do that, and Martin, please tell me if this is a bad idea, because it doesn't seem to be to me, is you can just have the implicit val JSON format equals this. Give a pointer back to yourself, inside of yourself, and that satisfies the compiler to look at that when you need a type class. This works. I don't know if it's going to blow up the Scala compiler at some point or something like that, but it hasn't done so far. So this is a pretty neat way, and I'll show you why that matters in a minute, so that the kind of streamlined way you get. Now, I can write a write method, and now I can use my unapply, because I know the types, and I know what I'm going to get back from that. And if the unapply works, which I'm going to assume it always will, I can just convert that into a JSON array or something more sophisticated and do the JSON serialization out. Same for read. I haven't filled it in because I ran out of space on the slide, and I'm not going to do all your homework for you. But it's easy enough to do the same thing with read. You just use the apply method that you've got. You know the apply method's there. You give it 2 values. It gives you back the type that you want. So the reason we do all this is so that we can do something like that. So this is now a fully JSONable case class in our system. Okay? All you have to say is case class person, name of string, age of int, bog standard case class, and then you say object person extends db object 2. You need to give it the types. This is the boilerplatey bit, and I think after looking at some of the macros talks here, I'm pretty sure I can get rid of that and do this in a macro as long as I'm inside of an object, so I'm going to try that next. But for now, this is really easy for anybody to get, and again, it's great for the bioinformaticians because there's really only one way they can write this, and it leads them through the process. They don't get this wrong. I've never had somebody say, hey, this isn't working, why not? They just get this. They're able to use it straight away. So that's the thing. Now we extend the type class. That's the companion object. It automatically gets looked at because the reference to ourselves is inside of us implicitly, and so it knows it can use that as the type class to solve the problem. Make sense? Good, because that sounds like a lot of weird concepts all looping around one another to me. But anyway, there's an example. And you can see I've also got the manifest. In real life, it doesn't just return, it's quite a bit more sophisticated than this. We've got the manifest, so we know all the type names and everything. All of those can go into the JSON that's output, and they can be checked against the JSON that's coming in. Once you've got that manifest, you can use it for a lot of different things. So, okay, tag types. I'm a bit short on time, so I'm just going to say very quickly on tag types. I use them myself, but there are problems with using them as part of a public API, and it's basically this down at the bottom here. You get types spit out in compiler errors that look like that, and that confuses people who aren't used to Scala. Okay, they see, instead of saying you need a kilogram and you've given me a double, what they see is you need a kilogram, you need an at double kilogram, and you've given me a double, and it's just a bit weird. Okay, they're not used to seeing types like that. So tag types, I find them useful for keeping me on track. I don't think that they make a good public API for people who aren't really interested in basically what you're interested in. So, okay. Another one I'm going to skip over pretty quickly, but another thing that I found with writing DSLs in particular is the cautious use of mutability. Just sometimes, Immutable builders are great, but just sometimes there's something that is either slightly nicer if you allow some mutability, or is just a lot quicker if you allow mutability. And in those cases, mutability is okay as long as you control the scope of it. And that's really, well, I think Runar might disagree, but we'll have that chat over beer later. But as long as you tightly control the scope of mutability, it can be very useful. And one of the things you can do is basically create something mutable in a method, okay, but using the loan pattern, take a function that takes one of those mutable things, does something with it, and then returns to the function, the controlling function, which then makes an immutable copy of it, and that's what you get back. Now you haven't got any of the problems of threading, for example. It's a local variable for this one case. You then, make a very elaborate DSL that uses all the mutability, makes it look really, really nice. But what you get out at the end of it is never mutable. You're always you're handed back something that you can't change. So basically, create the thing mutable, loan it, use it. After it's finished, freeze it, and get it back to the person as a fixed or immutable thing. Okay, and that's an example in a library that I wrote actually a couple of years ago now called Subcut, and that's the kind of idea here. The whole module, binding module, is immutable at the end of this, but while you're setting it up, just for the convenience and the clarity of the DSL, the thing that you get loaned, the module there, is mutable. So you can just bung anything you want in there, and then it reaches the end, and it becomes an immutable thing. So, okay, and very quickly, and this is the other thing. So actually, the cake pattern kind of got beaten up in the last session I was in. Was anybody in the 10 years of Scala? Okay. I got to say that I agree with almost everything almost everybody says in the Scala community, but I never really understood quite why cake was so popular. It seemed to me there was always an easier way to do this. And, for this, implicit parameters just seem custom made for this problem of getting items into classes or into functions. And I've been saying this for years, and I've been using it for years. It works great, but it's never caught on, and I think the reason is it doesn't have a snappy name. So I've decided to call this Parfait now, in the hope that it will get some of the attention that cake has got. But it's actually ridiculously similar to cake, just using implicit parameters instead of trait mix-ins and module objects, basically, to wire it all together. And it seems to perform pretty well as well, particularly in the compiler. And you get all the same advantages that you get of compile time verification. So here's the idea. You start with general traits that are abstract. You have implementations, concrete implementations of them that fill them in with real implementations. So we've got a DB, we've got a weather service, web service, and we've got forecast.io and weather.com, whatever, there. You have a DB config trait. So we have a DB config trait, and all that does is defines a DB. And we have a weather web service config trait that just defines, and it doesn't define them, sorry, it just declares them. leaves the definition elsewhere. So we have a DB config and a weather web service config. And you can then start mixing these things together. If you have a system that commonly uses, you can actually say, I want DB config with weather WS config if you want to do that. But if you're doing that a bunch, you probably want to combine them into a single trait. Like this is the weather, in this case, the whole system config, but it could just be weather and DB config or something like that you put together. Now to use it, we have a class that, it's called DB-doer. It does something with the database. This guy just says, I need an implicit DB config defined, okay? Then it can use the fields from that. It's all type safe. They've got to be there. Everyone's happy. Compiler takes care of all that. The weather does a similar thing, but says, okay, I need the weather config there. And that now has the weather config. Now down here, we've got a trait called temp doubler. That guy, you can make a couple of decisions with traits. You can go with the current idea or the current kind of cake way of doing it, which is just to define abstract fields that you need. And any concrete class will have to fill them in terms of the configuration that they've been handed, you'd hope. Or you could actually, down here, use an implicit of one of those types, like DB config or weather config. Now, if you do that, you've got to be careful about the naming, because if you mix two of these traits together and they use the same name for the configuration but different types, it won't compile anymore. I mean, it won't compile anymore, but you still want to be careful of that if you're mixing your traits a lot. So you probably want to call them something like, DB, lowercase DB config of type DB config, lowercase weather. I tend to use this one, just stick the fields in there as abstracts and use them. And then our total system, what that says is I need a config of the whole system. And we fill in the DB and the weather. Now, the nice thing about this is that whole system config is already a DB config and a weather WS config. So when we ask for classes that need those implicitly, those are satisfied already, okay? They're part of the super type of that class. So that's all taken care of. They get injected with the configuration they need. And that's really it. It's dead simple. It just uses implicits instead of having the necessary outer object for the module, and then kind of the definitions in there, and then the inner traits that the cake uses. I think this wins a little bit on boilerplate. It's just as safe, but I think what I've seen mostly is it seems to compile a lot faster. It doesn't seem to put as much strain on the compiler. So this is a fairly easy one. Right, and so that's Parfait, and then when you want to test it, dead simple. Oh, the other nice thing about this is it's more flexible at kind of not runtime. It's more flexible when you're working your way down through the system, because at any point, if you want to, you can actually change. You can make a copy of the existing bindings, but change them slightly, inherit from them, and just introduce a couple of new changes to it, and then pass that along as the implicit. So you can actually change things on the way down if you want to do that. And that's very useful for tests, because here we can just say, okay, now I'm going to bind in MySQL DB and forecast IO weather WS in this, and that's the configuration for that guy. Or we could bind in fakes or mocks or anything else we want to do. And there's the example that uses Postgres and weather.com. Okay, so bang on 45 minutes. Any questions, any thoughts? And in particular, I like collecting these. There were a couple I left out anyway, because I thought it would take too long, but I'll probably put those up in a blog post or something. And in particular, any contrary experiences, because like I said, these are based on things that work for me, but I've had a couple of these that, like the loan one, for example, I used to use that everywhere. Now I'm a bit more careful about where I use it, because I never thought somebody would return the thing they were being loaned. That one, and I'm like, well, yeah, of course they would. It's right there. So anyway, yeah. Questions or yeah, and I'll repeat it. So.
It's not a real question. It's more of an advertisement for a pattern.
Oh, okay. So this is an advertisement for a pattern.
Yeah, it's something that I read on the mailing list.
Okay.
It's regarding the unlikely names for implicits, so that they don't clash.
So using unlikely names for implicits so that they don't clash.
How to do that?
Okay.
Someone suggested using backticks, and then you just write like even a sentence there. So if you have
Ah,
Type instance. You don't try just JSON format something.
okay.
Okay, this is how we JSON format this.
So that's really interesting. Okay, so if I can paraphrase, one of the problems that you have when you use a lot of these kind of abstract, and this is a problem with all of these, it's a problem with Cake as well. If you just say a field DB in a trait, and then you have another field DB in a trait, sometimes when you try and mix these things together, they types clash, and you get problems of like these names that show up. And so the problem is one of basically name clashing. And what you're saying is you can do this. Scala lets you do backticks and then use all sorts of crazy stuff in names. So if you put any identifier in backticks, you can use spaces in there. You can use dashes, I think, and dollars and all sorts of things. So you can actually write a sentence in there that says something like, instead of dbconfig, you could say, this is my DB config for MySQL, I don't know, or something like that, and have a full thing in there. Then you're never going to get a name clash with that or with a field that somebody wants to use. That's the other thing about DB in a trait. You've now consumed that, and somebody who then wants to use your trait in a class, they can't really change what that means anymore. The DB's gone. That name has gone. A bit like a keyword, but more localized. So yeah, that's a good tip. I like that. Ah, okay. So, and this is okay. So you're saying it's specifically for implicits where you're not going to use the name anyway, right? That's actually one of the reasons I tend to, even though I know style says you should, if you're going to use the implicit, you should actually use an implicit parameter rather than context bounds. I tend to use context bounds when I can anyway because it doesn't consume another name, and then I have no problem in saying implicitly in the code, and so I just use implicitly to get it. In that case. But I know that's a style thing, and not everybody agrees. So, yeah. Okay, yep? Can't you use any val? Yes, yes. So, yeah, the question is, can't you use any val instead of a tag type? Yes, in some situations you can. And that's actually, any vals, I should have mentioned that, actually. That's definitely a pattern I use all the time. Any vals are a natural way of getting just the same efficiency. I think the other thing tag types give you, though, is they give you ever so slightly more convenience because you now don't have to dereference like the value in the thing. The tag type really is a double. But that's also a downside to them is when you're using them, sometimes, well, actually very often, those tags sort of disappear, they evaporate, and suddenly you're just dealing with a double anymore. Like if you took that, I think I have an example here. If you take that kilogram, which is at of double and kilogram, if you multiply it by 2, you just get a double back. The tag has evaporated at that point, which, again, another reason I wouldn't use it in a public API, because that's confusing behavior to somebody who doesn't know the reason behind it. They're like, well, it was one of those types a minute ago, and now it's just one of these again. So that, yeah, good point. Any val, extends any val, if you can use it, is fantastic, because you get all the efficiency back again. That's what tag types give you. They give you slightly more convenience and the efficiency back of not boxing everything. All right, well, if I don't see anything... Yeah, oh, no, just an itchy head. Okay. Well, thank you then for coming. I hope that proved to be of some use. What I didn't really say is that query, in particular the query examples, are based on a real-world situation where that query is fed into this monadic, free monad-based kind of couch DB library that's used, and it fits really well. And it fits in particular because it's not another monad that I have to worry about nesting fors or anything like that to use it. It's just a simple builder. You get the thing out, you chuck it in to one of these primitives, which is basically query the database, and you get back a result. And one of the things I'm going to be tackling fairly soon again is attachments, which are another kind of big subgroup of couch. And when I do that, I'll do the same thing. Instead of having multiple different concrete data types in the monad that deal with binary attachments and text attachments and multi-line and single line and stuff like that, all of that will be constructed in a case, basically a bunch of case classes that describe what it is I want to get back, and then there'll be one get attachment. And everything it needs will come from that definition that I've built up. And that's a really nice API for somebody to use, because they're just like, okay, I need an attachment, and it's a text-based, and it's multi-line records, and here's the formatter for it. Another thing you can throw in there is the type, so we automatically format it to and from this type. And all of that stuff can be built in there. And then the handler in the monad can just say, okay, well, I know what I'm dealing with here. That's what I'm going to give them back. So it integrates nicely. All right, thanks, everybody. And